In this video, FM synthesis will be explained using Kiloheart's phase plant synthesizer, as well as Ableton Live's operator. FM synthesis is a synthesis technique where an audio rate oscillator modulates the frequency of another oscillator in order to generate a new sound. Audio meaning what we can hear. Sound is made of oscillating air pressure. To oscillate is to move in a back and forth motion. Frequency measures the rate of this motion. Frequency is the F in FM, and modulation is the M. A modulator is a signal we can use to change or modify another signal. In other words, in synthesizers, we can use a modulator signal to modulate another signal. In synthesizers, we use modulation to change parts of a generated sound. We can think of synthesizer signals as comprised of signals that are generating sound and signals that are creating changes in a generated sound. If you use an oscillator that has the potential to generate sound, to modulate the frequency of another oscillator in order to create a new sound, you are using FM synthesis. Sound is made of combinations of oscillating waveforms. With sound, we measure these oscillations in hertz. How many times a second a waveform is oscillating is the waveform's frequency. If a waveform has a frequency of 40 hertz, it is oscillating 40 times a second. In other words, the waveform completes 40 cycles in 1 second. A cycle is an air pressure change that moves from high pressure to low pressure and then back again. The frequency range where humans hear these oscillating waveforms is between 20 Hz and 20 kilohertz, kilo meaning 1,000. This is audio rate. This is the frequency range of sound. If an oscillator is set to oscillate between 20 Hz and 20 kilohertz, it can generate audio. In synthesizers, we call oscillators that oscillate below 20 Hz LFOs. LFO meaning low frequency oscillator. We do not hear LFOs. In synthesizers, we use them to modulate other signals. I will demonstrate modulating the frequency of an oscillator with an LFO in phaseplant. First, I will load an analog oscillator into phaseplant's generator section. This oscillator generates waveforms that oscillate at audio rate. In other words, this oscillator will generate sound. With this oscillator, we can choose between common wave shapes. I will select a sine wave, which generates the sound of one single frequency. With phaseplant, when hovering the cursor at the output of the oscillator, a green plus sign will appear. In phaseplant, devices that output audio, in other words sound, will be indicated by the green plus sign at the output. Devices that do not generate sound, like an LFO, can be loaded into phaseplant's modulator section. I will load an LFO into phaseplant's modulator section. When hovering the cursor at the output of the LFO, an orange plus sign appears. Orange plus signs and green plus signs in phaseplant indicate a signal that can be routed. Green plus signs indicate a signal that can output audio. Orange plus signs indicate that the signal will not generate audio, but can be used to modulate another part of the synthesizer. In other words, this LFO's signal can be used to modulate another signal within the synthesizer. If I select the orange plus sign at the LFO's output, other plus signs will appear within phaseplant's user interface. The plus signs that appear are currently all the potential places in this synthesizer that can be modulated with this LFO. We can see by the orange plus signs that have appeared in the graphic user interface of the analog oscillator that this oscillator has potential parameters that can be modulated, including parameters that control the frequency of the oscillator. The parameters in this oscillator that control the frequency of its signal are the semitones, harmonics, and shift settings. If I select the plus sign at one of these places, the LFO signal will be routed to this location. We can see the virtual signal routing by a dashed line that appears. I will select the harmonics frequency settings for modulation. These settings change the frequency of the oscillation by harmonic values. We can see the virtual routing from the LFO's output to the harmonic settings by the dashed line that appears. With the LFO signal routed, if an amount of modulation is set, this LFO will modulate the frequency of the oscillator. An amount for the modulation can be set by dragging in the small circles at the routing's input or output. With frequency, the amount set determines the range the frequency will be modulated in. Remember, the frequency range of sound is from 20 Hz to 20 kHz. With various potential amounts set, the frequency of the oscillator will change within this range. Once a routing is established and an amount is set, when playing a note, because of the repeating signal change of the LFO, we can now hear the sound of the oscillator's frequency changing up and down, repetitiously between high and low frequencies. We can see in the LFO, indicated by the moving ball, how the LFO signal is changing over time, and how this relates to the sound we hear, specifically how the frequency changes, which is what the LFO has been routed to modulate. This type of modulation is common in synthesizers and can be commonly used for vibrato-like sounds. When using LFOs to modulate frequency, we can hear that the frequency change is happening over time. But what if the frequency of the LFO is changed to a frequency above 20 Hz? What would we hear then? In other words, if the modulating waveform goes above 20 Hz into the frequencies of sound, what will happen to the sound of the waveform that is being modulated? Let's test this out. This LFO goes a little bit above 20 Hz. I will slowly raise the frequency above 20 Hz. Listen as the frequency of the LFO crosses over 20 Hz. When modulating frequency, once the modulator's frequency goes above 20 Hz, we can no longer hear the modulated change in frequency happening in real time. What we hear is newly generated frequencies in the sound. With the LFO below 20 Hz, we can track the frequency change with our ears. But once the LFO crosses 20 Hz into audible frequencies, we can no longer track the frequency changes because they are happening at too fast of a rate. Instead, what we hear is a more complex tone with added frequencies. This is how FM synthesis works. Let's now change the modulator from the LFO to an audio rate oscillator. To remove the modulation routing from the LFO, you can double-click the small circle at the routing's output. Now, in Faceplant's generator section, I will load another analog oscillator. I will once again choose a sine wave which generates one single frequency. I will route the output of this sine wave oscillator by selecting the green plus sign at its output. The green plus signs that appear are all the current places in the synth that can be modulated with this audio rate signal. In the same way I routed the LFO, I will route the oscillator signal to the harmonic settings. Once again, the harmonic settings scale the frequency by harmonic values, which are good for FM synthesis. While playing a note and increasing the amount of the modulation by once again dragging in the small circle at the modulation input or output. When we do this, we can hear that the sound changes. But rather than hearing the frequency of the sine wave going up and down, what we hear is added harmonics in the sound. We no longer hear just one single frequency. What we hear is a new tone that contains other frequencies. These newly generated harmonics are the result of the frequency modulation. It is possible to set the modulating oscillator below 20 Hz. If I set the harmonics to 0 and increase the shift settings with the modulation still routed, we are once again able to hear the frequency change happening over time. By setting the oscillator's harmonic value to 0 and with frequency values below 20 Hz, we have essentially turned this oscillator into an LFO signal. While increasing the frequency, we can hear the point where we cross 20 Hz and new frequencies enter the sound. If we do this while using a spectrum analyzer, we can see exactly what frequencies are coming into the sound and at what modulation amounts make this happen. Specific sounds like that of horns, guitars, or flutes, even sounds that are not necessarily meant to be musical, all have different combinations of frequencies that sound at the same time, giving its sound its unique quality or timbre. Timbre is a word that describes a sound's unique character and specific set of frequencies. Harmonics are a specific set of frequencies that are common in musical instruments. With FM synthesis, if the modulating oscillator and the oscillator generating the sound are set to harmonic values, the results of the FM will generate harmonic frequencies. This is one reason why you may choose to modulate the harmonic settings in Faceplant's analog oscillator. If I set both oscillators to generate sine waves and set their harmonic values both to 1, when a modulation amount is set, the newly generated frequencies will be the harmonics of the sounding oscillator's frequency. If I set the modulating oscillator's harmonic value to 2, the resulting frequencies will be odd harmonics. The amount of modulation determines the amount and the amplitude of the generated harmonics. While changing the amount values over time, we can hear changes in the sound. Perhaps we could shape those changes to sound horn-like. Creating specific sounds with synthesizers requires a way to sound and shape many frequencies at the same time. Before FM synthesizers, we were using additive and subtractive synthesis to set and shape its sounds, using combinations of oscillators that generate different sets of frequencies and filters to shape those frequencies. With FM, we are able to generate complex tones that don't require many oscillators and filters. With just two sine waves, one a modulator and one being modulated, and by setting different modulation amounts and at different frequency settings, we are able to create a variety of much more complex sounds. This is at the heart of how FM synthesis works, for shaping and creating changes in a sound. In FM synthesis, we call the oscillator doing the modulation the modulator, and the oscillator being modulated the carrier. Having just one carrier and one modulator using FM can be just what you are looking for in a sound. But sound design using FM synthesis often contains many modulators and many carriers, with different routings in order to design a sound in more complex ways. Commonly, with FM synthesizers, like the classic DX7 or Ableton Live's operator, modulator carrier routings within the synthesizer are pre-routed and determined by a set algorithm. Because phase plant is a modular type of synthesizer, we can choose any routing we may dream up. But with classic FM synthesizers like the DX7 and Ableton's operator, the routings are predetermined. With synthesizers like these, you can choose a predetermined routing by selecting a graphic that determines the routing. With these graphics, the bottommost squares represent carrier oscillators, and the squares above represent modulators. With classic FM sounds, modulators are generally not part of the audio, meaning their audio is not routed to the output of the sound. Rather, the audio is routed to modulate set carriers only. With classic FM, modulators are routed to carriers. Carriers are responsible for what we hear and the amplitude of the sound. Generally, modulators in FM are not routing their audio into the sound. Rather, their audio is responsible for changing and shaping the timbre of the carriers they are routed to. In other words, the modulators do not generate the sound. Rather, they change the harmonic content or timbre of the carriers they are routed to. The carriers in FM are outputting the sound. If we look at these routing graphics in Ableton's operator, we can see how each of the squares represents the A, B, C, and D oscillators and how they are routed by the color of the square, either as a carrier or a modulator, modulators above and carriers below. If I choose this algorithm all the way to the left, I can use oscillator B to modulate the frequency of oscillator A. If the level of B is raised, which is the amplitude of oscillator B, this will modulate oscillator A, and newly generated frequencies will enter the sound. This is the same thing that is happening in phase plant when we route an oscillator to a frequency parameter of another oscillator and increase the amount of modulation by dragging in the small circles. Doing this is essentially increasing the level or amplitude of the modulating oscillator signal. One difference with this in phase plant is, by default, the oscillator that has been set to modulate is also routed to the sound's output. With the two oscillators currently in phase plant's generator section, and with the current routing, both the modulator and the carrier are being routed to the audio output, indicated at the output of both groups, with lane 1 selected. If I set each oscillator differently, and then turn them on and off, we can hear that they are both being routed to the sound's output. With classic FM and how the routings are set in operator, the modulating oscillator is only routed to modulate the frequency of the oscillator below. Its generated sound is not routed to an audio output. With this, we do not hear the sound of the modulator, only the results the frequency modulation has on the oscillator that is sounding, or in other words, the carrier oscillator. If A is set to be a carrier in operator and we turn it off, we will not hear any sound. Even though the level of B is turned up, we will not hear the audio without the carrier. In phase plant, when you insert an oscillator in the generator section, it will be placed in a group with an envelope output, where you can route the audio. By default, the group is set to output the audio to phase plant's effects lane 1, which routes to lane 2, then 3, then routes to the master output, where we can hear the sound. In phase plant, for classic FM, we need to set the modulating oscillator so its audio is not routed to an audio output. To do this, we can remove the default output of the modulating oscillators group by selecting the X in the upper left corner of the envelope output. This will delete the output from the group. Now when playing a note, we will not hear this oscillator, but we can still route its output to modulate the sounding oscillator, or in other words, the carrier oscillator. To stay organized in phase plant using FM, you may choose to name your oscillators modulators or carriers. These modulator carrier sets are useful for creating new timbres and harmonic content in the carrier oscillator sound. But what makes FM synthesis work as a sound design tool is having the ability to shape the harmonic content over time. To do this, we need a way to control the amplitude coming from the modulator. If we look at operators' oscillators, we will find that each oscillator has its own amplitude envelope. Each oscillator A, B, C, and D has its own envelopes that can shape the amplitude of each oscillator's audio output. When we choose one of them to be a modulator, the way its envelope is set will shape the timbral change of the oscillator it is modulating. For example, quick attack and decay settings can create transient timbral changes, and slower settings can create more evolved timbral changes. Trying different envelope settings at various modulation amounts with just one modulator and carrier is a good start for listening to and understanding how FM can affect a generated sound. To set this up in Faceplant, we need an envelope. I will add an envelope to the modulator section. This envelope signal can now be routed to modulate the audio output signal coming from the modulating oscillator. I will select the orange plus sign at the envelope's output. Since we already have the modulating oscillator's output set to modulate the frequency of the carrier oscillator via the harmonic settings, which we can still see is set by the virtual routing's dashed lines, we will see a yellow star appear below the orange plus sign at the harmonic settings. Select the yellow star to route the envelope's output to the signal coming from the modulator. This will allow you to modulate that signal with the envelope. When we hover the cursor over the small circles, we will see a yellow dashed line appear coming from the envelope routed to the signal path of the modulator's output, which is indicated by the green dashed line. The yellow dashed line shows that the signal path going from the output of the envelope to the green dashed line, which indicates the modulation routing from the modulator to the carrier. This shows that the envelope signal is modulating the signal coming from the modulator. This set envelope modulates the amplitude of the signal coming from the output of the modulator. Once again, how the envelope is set will determine how newly generated frequencies will enter the sound, and how we can use the settings of the envelope to shape the timbre of the sound. This is similar to how using an envelope to modulate a filter in a subtractive synthesizer shapes the timbre of the sound. Once again, beginning with just one FM modulator and carrier is a good starting point when trying to understand the nuances of FM. But as you would guess, FM sounds can be much more complex. The same way envelopes can be used for shaping the timbre with FM, you can also use LFOs, or any other modulator you choose. You can also add other modulators or carriers. The way you route their signals will determine how they are affecting the sound. If I add another analog oscillator and route its signal to the current modulator's frequency settings, this is like having a modulator above another modulator in an algorithm. With this, the way it shapes the modulator below will then in turn modulate the timbre of the carrier. Having multiple modulators can give you more options for shaping the sound. If one chooses to, the current default envelope output can be used to shape the amplitude rather than adding another envelope in the modulator section. We can do this, but remember, by default, the oscillator is currently being output into the sound. If you choose, you can change the output of the envelope here in the bottom right corner and change it to sideband. This will remove the signal from the sound. There are many options for signal routing in Faceplant, and a lot more we can do with FM and its architecture, as well as using any other sound generators Faceplant has to offer. There is a lot more to discover with FM synthesis, but no matter how you will use FM in your own sound designs, and with whatever synthesizer you may be using, the basics of FM will remain unchanged.